what I was going to do was I was going to start off by explaining your second assignment. Okay. Your um, uh, your the assignment should be available for you to view on Moodle. Can you please double check to confirm that it is available and accessible to you? All right.
Logging in now.
Okay.
1 assignment 2. This is the document, all right. Okay.
And you have the upload area as well. Yes.
The upload area is
15th April,
visible
eh?
right now.
Excuse me.
15th April.
The deadline. Yes.
Okay.
Upload area is all right as well.
All right. Cool. Okay. So essentially, this assignment is very similar in structure, at least, to your first assignment. All right. Your first assignment was about the ping utility. This one is about the traceroute utility. All right. So essentially, you're going to learn about the traceroute utility, and you're going to conduct a simple experiment. Play around with it. The assignment is worth 15% of your overall mark, worth around 15 hours, and your deadline is the 15th of April. All right, which is after your examinations. Okay, so you would be able to have some time to work on it even after the assignment. All right, this is the latest date that I could actually set this assignment. So at least I've given you more time and more leeway for you to work this out. So essentially, what you're going to do is you're going to learn about the traceroute utility, conduct some experiments, as well as do a little bit of research. All right, making use of academic sources. Obviously, you're going to be needing to upload your work in a PDF format. All right, like usual. All right, make sure that it is written in correct English. All right, and make sure that you have your references and citations in the format that is taught to you in the personal development program. All right, each and every one of you should have access to the personal development program. All right, so it is important that that you make use of that resource in order to help you know how to reference. All right, obviously, the whole point is so that you avoid plagiarism. All right, therefore, allowing yourself to be better trained in the art of academic writing. All right, and which will inevitably help you in further studies. So, this is your assignment in question. So, the assignment builds upon the work done with the ping utility in coursework 1 by exploring another utility within the Internet Protocol or IP suite. All right, this is the traceroute function. All right, for this coursework, you need to do some background research on the utility to become more familiar with it. All right, you need to conduct research on the traceroute utility, and you need to provide some background upon what it is and what it's attributed to. All right, and you should write around 300 words using proper citation and referencing techniques. All right, about the traceroute utility. Then, all right, part 2, you need to explain how it can be used. All right, providing some form of syntax and parameters, and explaining using screenshots, all right, and referencing accordingly how it can actually be used. All right. So that's very similar to what you had to do for your first assignment, essentially. The second part, all right, or part B rather, all right, you are asked to conduct a little bit of an experiment, all right, in which case you first and foremost need to identify your IP address, all right, to indicate where you are located geographically, all right, and ideally, again, use screenshots in order to showcase that what you're showing is actually true. All right. Then the second part is that you need to select two web addresses, all right, two locations, one from Oceania, all right, the region known as Oceania, and another one from South America. All right, these locations can be chosen, or rather, must be chosen from a different set from the ones that you used for your first coursework. However, um, they can be they like with your first assignment. You need to make sure that they are actually hosted in different locations. All right, and also make sure that you indicate the case by using screenshots to show that they are from different geographic locations. Once you've selected these two locations, all right, you're going to apply a traceroute utility to each of these sites, obviously from your machine, all right, and then you're going to plot the path taken for packets, all right, on a world map tracking the IP address from one hop to the next. All right. Essentially, you need to include screenshots for each hop that is happening for these packets that you're sending. All right. Um, uh, so you're going to be probably providing a number of screenshots for these different hops that are actually happening for your data packets. Then you're going to be asked to comment on the results of your experiment. However, it is sometimes going to be the case, all right, that the trace route process might actually be blocked out. It will be okay if it happens one or two steps, if you will. However, if it's more than a number of than two or three steps, then I would suggest that you would look out for a different location and apply the trace route on that. Okay. Um, so that at least you wouldn't invalidate your experiment. Okay. So you need to, sorry, if not more than two. So if you have three or more hops, then essentially you need to find a different location, all right, or a different website. Okay. So essentially, that's what you need to do. Like with other assignments, you have been provided with the template. All right, you need to make sure that you use a cover sheet showing all of the relevant details of this assignment. Include a table of contents. All right, provide an introduction where you're describing what somebody's actually going to be reading throughout the rest of your report, your answers for part A and your answers for part B, all right, including references and citations, as well as links to tools that you might have used, all right, as well as a conclusion where you briefly outline what you did, all right, and being an academic exercise, you should all explain um, um, what you learned from this assignment and what you might have found challenging and how you tackled it, essentially. All right. So again, make sure that you use subheadings in order to split your report into its relevant subsections. All right. Nobody likes to read one long essay. All right. Start each section on a new page. All right. Use diagrams when necessary. Use the template that we've given you, and all information, including diagrams, must be labeled and referenced accordingly. Obviously, do make sure that you perform a spell and grammar check, all right, before submission. And obviously, when it comes to referencing, make sure that you're using valid academic references. Okay. So the marking scheme for your assignment is split up accordingly. So you have 5% of your marks dedicated to the introduction, 20 for part A, 60 for part B, 5% for inclusion, 5% for presentation, and 5% for references. Do you have any questions with regards to this assignment? Yes. But the trace utility is a different type of utility. All right. Yeah, no. What I meant by 2 or 3 hops, what I meant was 2 or 3 hops which are hidden. All right, as in, so if so, you might have a number of hops which are blocked. They're hidden. All right, if they are blocked, so if you have 3 or more which are blocked, so you don't know what route was actually taken for more than three or more hops, all right, then essentially the experiment becomes invalid, all right, as in if you manage to do it, if you manage to find a website and the trace route utility only had 2 blocks, all right, then that's fine, all right. Not necessarily. It will just show up as though it's hidden essentially. You'll have a number of you would know that there was a step that happened, but you don't know where it actually went through. So, for example, it might have passed through a particular server, you know, which doesn't allow that. Yeah, that's essentially what happened. All right, all right. Any other questions, guys? All right. Like with every other assignment, if you have any questions whilst you're working out on this assignment that you would like to ask me, please feel free to send me a message on Moodle, Discord, or whatever. All right, I will be more than happy to help you out. Okay, so with that done, um, I would also like to give you your first portion of homework. All right, essentially, it is going to be reading from your part. All right, if you remember, in class we had already talked a little bit about different types of topologies. All right, however, there happens to be a set of slides which go into a little bit more detail about network topologies and how they can be structured and how they can be set up and so on and so forth. All right, which is this one, all right, called Networks and Internet Part 4, all right, which, if we have to take a quick look on Moodle, so it would be this this link over here, this networks and internet. Part 4, I would like you to take a look at that and read it in your own time. Notice that we've already discussed all of these elements in class. All right. The only thing that we might have not discussed is the idea that some topologies can be defined in a physical implementation as well as a logical one. All right. So logically, you can have a network topology which might not necessarily reflect the topology which you have implemented physically. So that is also a thing. But essentially, over here you have the 6 basic topologies, all right, and you have diagrams of what they might look like, all right. What are their best assets? What are their features? All right. What are their limitations? All right. Different variations of those types of systems. All right, as well as advantages and disadvantages. All right. So I would like you to take a look at these slides. All right, and read through them in order to bolster the information that we've already talked about in class. Okay, so that you will be able to move on to yet another topic. So today, so that was the first one. We're going to start off our lesson, all right, by discussing the difference between packet switching and circuit switching. We've already discussed this again in the past, all right. However, let's further define it in today's lesson. Essentially, what we're going to be looking at is the different types of switching networks. Essentially, the networks that are used in order to transmit data over long distances. All right, we're going to be looking at a number of switched nodes, all right, or switches along the path, all right, where our data is going to traverse, and we're going to have end devices which we're going to know as stations. All right. Now, a station can be anything from a computer to a terminal to a phone, whatever. All right. So essentially, an end terminal. All right. We're going to be calling a station, and the nodes in between essentially are going to be our switched nodes. Now, essentially, a node can be either connected to yet other nodes, or they can be connected to stations. All right. But in our case, what we're going to be looking at is the two different techniques and the two different technologies which are used in order to transmit a message. All right, we're going to be first focusing on circuit switching, then we're going to be looking at packet switching, and then we're going to be looking at message switching because it's very similar to packet switching to a certain extent. All right, it is sort of like a hybrid between the two, if you will. All right. So let's start off with circuit switching. All right. So circuit switching essentially is the situation whereby you have a dedicated connection between two stations. All right. So whenever you're going to set up a circuit switching communication, you need to pass through 3 different phases. First, you need to establish the connection, then you transfer the data, and then you disconnect. All right. Essentially, whenever you have set up a um, circuit switching communication, the end stations will have full access of the entire capacity of that particular channel. All right, and nobody else will be able to use that same channel whilst they are using it. All right. This kind of switching is very, very, very similar to the old style telephone system that used to exist in the past. Nowadays, we don't really use this particular implementation because it is rather inefficient. However, for those of you who might remember, all right, in the past, whenever you were whenever you picked up the phone, all right, and you dialed the number to your friend, your colleague, or whoever, all right, essentially you were um, linked with that other person via a hard circuit, all right, which nobody else could be making use of any part of that circuit at any given point in time, all right. In fact, if you go back even further, all right, whenever somebody needed to call somebody else, what they would do is they would pick up the phone, they would speak to an operator, all right, and the operator will then connect them, all right, to their destination. They might also connect them to yet another operator, who in turn will connect them to their destination, and then they would be able to perform their communication. Essentially, they would be able to talk over the telephone, all right. Um, in the past, this was done manually. All right, so essentially, the ability to switch from one circuit to the next was actually done by a physical person. All right. Eventually, they actually introduced machines that acted as these operators. All right. However, these kind of machines needed to act intelligently. All right, and in fact, what they started using was the idea of phone numbers. Before then, phone numbers weren't really a thing. All right, the number itself was then used in order um, uh, to help the system switch to switch accordingly, essentially. All right. At first, it was mechanical. Eventually, it became digital. All right. So that was essentially how circuit switching um, um, uh, was established. Well, essentially, what this telephone network was doing was it was creating a circuit, a path, all right, from one station to the next, all right, so from one telephone to the other, all right. Um, but the important part behind this circuit switching um, um, circuit when the circuit was established was that the two individuals who were on the phone at that particular point in time were able to make use of all of the resources. All right. Now this is somewhat inefficient for the simple reason that you're not really using the entire bandwidth all the time. All right. Even if I, for example, if we take, for instance, this communication that we have over here, all right, it is also the case that I might pause for a breath, for example, or pause in order to restructure my thoughts before I actually communicate with them to you. And in those split seconds where I am silent, all right, essentially we're not actually sending any data to and from, at least not via voice, at least, all right. I might be sending other pieces of information, but I might not be using the full capacity of the signal, if you know what I mean. So if we had to take a little bit of a look at how this would work, all right, as a diagram, all right. So let's say that source A will needs to communicate with destination B. This would be our network of nodes. So the source would communicate with the first node. A path would be established, and then the communication would be able to occur. So what would happen if you have more than one um, connection that needed to be established? Well, in that case, you would need to find an alternative route. Now, notice an alternative route can pass through the similar nodes, but it cannot use the same path at any point in time. In fact, um, it could be the case that the transmission distance, all right, or the distance that you're actually going to be transmitting the data from point to point, will actually be by far greater than the geographical distance that you're actually calling. All right. So, for instance, If I were calling somebody living in the same village that I lived in, it doesn't necessarily mean that the signal that I am um, that I am using is actually passing just through my own village. It might be going out of town through a number of different towns and then coming back into my own village because that might have been um, uh, the only available path for me. All right. Now, in this kind of difference, all right, between transmission distance and geographical distance, in the past used to also throw up uh, problems with regards to billing, essentially, all right, because you might actually be charged extra because the 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 circuit that was established was actually outside of a particular billing area, and then when it actually came back in, you were charged for a long distance call. All right, but in more modern times, all right, all charges in this case were usually determined based upon the geographical distance in which a phone call was actually made. All right. So if we had to take again two examples, so we have A trying to communicate with B and C communicating with D. If C started communicating with D, all right, a possible path that might have been established might have been this sort of like blue line. If A needed to communicate with B, notice we can use the same or similar nodes, all right, but we can't use the same path. All right, is this clear, guys?
Yes.
All right. So, um, so essentially, as you can see, when it comes to circuit switching, we have a little bit of an inefficient system, because obviously the channel is going to be dedicated for the duration of that connection. So even if no data was actually being passed through those two nodes or those two stations, sorry, then essentially capacity was wasted. You also have the additional overhead of setting up the connection, which takes time. For those of you who might remember, all right, whenever we had the dial up internet, what we used to do was we actually had to set up the internet connection. Nowadays, we take it for granted. We're always connected to the internet. We don't actually need to set that up. All right. And once we're connected, transfer was pretty much transparent. All right. In fact, this kind of system, as we said, was predominantly used for the phone system, and it was established in order to guarantee an element of quality of service. All right. Nowadays, we don't particularly use circuit switching for the simple reason that um, uh, that it, it's it has been superseded using packet switching. All right, we'll talk a little bit about that in a bit. In a bit. But whenever we're talking about circuit switching, and whenever you might be reading about it, you might probably come across certain different terms. All right, the subscriber is basically the person who is actually connected to that network. So, for instance, if I was connected to Maltanet, just to give you an example of what it used to be like in the past, all right. As a telephone subscriber, I was connected, so I was a subscriber to that network. All right. Now you might have what is known as a subscriber line, where you might have, for instance, a local loop or a subscriber loop. All right. All of which have a connection to the network, and they might be set up within a few kilometers or maybe tens of kilometers of each other. So you might have direct connections with several different entities inside. Usually, however, you would also be connected with what is known as an exchange. The exchange is essentially um, uh, the center whereby switching actually occurs. All right, essentially in the olden days, all right, on the old timely telephone with the telephone operators, essentially the telephone operator worked in an exchange. All right, they were the ones who were doing the circuit switching from their end. Okay, they essentially help, all right, or they're there in order to be able to set up connections between one subscriber and the next. All right. And then between exchanges, all right, you might have what are known as trunks. Essentially, trunks are branches that connect one exchange to the next. All right. And they're also multiplexed, essentially allowing multiple connections to happen at the same time. All right. Okay. Between different exchanges, obviously. All right. So that is those are essentially some terms that you might come across when you're looking up circuit switching. Let's now talk a little bit about packet switching. Now, packet switching, the whole point behind it is to make better use of the network or infrastructure that we actually have at any given point in time. So essentially, the way that it works is we take the data that we need to send and we break it up into small pieces, small packets. This is why it's known as packet switching. And each packet essentially is sent over the network and routed through the network, all right, giving it a destination, all right, so that they would reach the destination, but not necessarily making use of the same path or the same um, uh, duration. Now, not every piece or not every packet is going to be the same sized, all right, or it might not take the same path, all right. Essentially, what packet switching is going to do, all right, is it's going to transmit these packets, all right, from source to the destination, and then it would be the destination's responsibility to reassemble, all right, the the package, all right, or the data itself. Okay, um, it's kind of like if we all met up in one location. I said, okay, guys, we are in this location, let's say at St. Martin's, for instance, and I told you now we need to race to Chirkawa, for example. All right, as an example. Um, if all of us take different routes and all of us take different roads to get there, we might all arrive at different times, even if we leave in a particular order. Doesn't necessarily mean that we're going to arrive at that same order. All right, and that is exactly what packet switching is all about, essentially. Okay. Now, what happens when we're actually creating a packet? What we're doing is we're adding additional information, all right, to the piece of the piece of data that needs to be transmitted, the payload, essentially, that we want to transmit. And we introduce a header which includes several pieces of several pieces of information which is important for this packet to actually arrive at its destination. First and foremost, it needs a destination address. It needs to know where in the sequence it needs to fit, other information of that sort. All right. And then it would need to arrive at its destination. All right. So the just like it might be the case that we might take different routes, all right, in our fictitious race, um, uh, because of traffic jams or because uh, we found certain roads were more busy. We maybe we had big cars and we couldn't actually fit down very tight roads, whereas somebody on a bike would be able to fit down tight roads, and so on and so forth. All right. The same thing can happen to these packets. Packets might have shared destinations, but they might take different or multiple routes in order to get there. All right. In fact, this type of switching is known as a connectionless switching because the sender and receiver don't necessarily need to dedicate a particular route for that data in order to get from sender to receiver. In fact, most WANs, all right, make use of packet switching, especially when we talk about the internet. All right, we're currently making use of packet switching ourselves. All right. So essentially, what packet switching allows us to do is that it allows us to have variable bit rates and variable data streams and variable um, uh, forms of communication happening over the same network. So essentially, we might have over a network cable, for example, have multiple packets for multiple different applications, all going down that same route. All right. And then we would traverse different nodes, all right, such as switches, routers, access points, and so on and so forth, in order to make their way from the source to the destination. The result of which makes the system more robust, more reliable, because essentially, if one route was blocked, then essentially you could take yet another route in order to reach your destination. And secondly, it makes better use of your resources for the simple reason that the channels of communication are not going to be hogged by a specific line of communication. All right. The only downside is that the receiver will need to reorder the packets, all right, as soon as they arrive, all right, in order to make any sense of the data that is being sent. So what does a packet need to in order to be able to reach its destination? So first and foremost, it needs to have the data itself. All right. Then it needs the destination address. It needs to identify who the source is. All right, because otherwise, you can literally flood in a bunch of data to a particular user. But if they weren't, if the connection wasn't actually established, then essentially you wouldn't accept that data, people coming in towards you. So you need to have not only the source address, but also the destination address, but you also need to identify who is actually sending this information. You need to also have a sequence number, all right, in order to identify in which order this particular piece of data um, needs to be placed. And also, you need to have some form of error control. All right, essentially, each piece of data you need to make sure that it actually arrives error free. If it doesn't arrive error free, then in most cases, if you're using, for example, the TCP/IP connection, which is the most common type of connection that we're talking about here, you would resend those packets that might have been corrupted in some way, shape, or form. All right. Essentially, with all of this data, all right, the packet will be able to make its way towards the various nodes, all right, in the network to its destination. So let's take into consideration this particular example. So over here we have one node or one um, one person in London who wants to communicate with another person in New York. All right. And these are the packets, all right, 1, 2, 3, 4, 5, that want to go through these packet switching exchanges. All right. Notice even the terminology is very similar to the circuit switching exchanges. So, for example, packet 1 might go into this packet switching exchange, to this packet switching exchange, to this packet switching exchange, which in turn arrives here. Packet 2 might have gone through here, to here, and to the destination. Packet 3 might have gone from here to here to here to here to the source. And packet 4 might have gone from here to here to here to here to there. And packet 5 might have gone from here to here to there. All right. So notice some might take the same route, some might take different routes. All right. The important thing is that we try to keep the flow as high speed as possible. All right, in order to make sure that the packets arrive at the destination intact. Okay. Obviously, it might be the case that certain packets might have arrived in a different order, in which case you would reorder them so that you would actually be able to make sense of the data that has been sent. Okay. Usually, essentially, what the packet switching exchanges will do, all right, is they would perform a very simple test. All right. So when a packet comes in to the packet switching exchange, all right, it will check its destination, all right, address with addresses that it has linked directly with that exchange. So you would say, is that address that I need to deliver this packet linked directly to this exchange? If yes, you will just send that packet to the end user. If not, you will just route it to another packet switching exchange, which will be more appropriate in order to deliver that message. All right. So essentially, um, uh, you would go through the packets one at a time in a form of queue. All right. You would see whether or not you're going to route it to something that is connected to it directly. If not, you would route it to another um, uh, to another packet exchange system via sending it via some form of output queue. All right, and this happens from packet to packet, from packet exchange to another packet exchange to another packet exchange until eventually it reaches its destination. All right. To a similar extent, this is basically what you're going to be doing with your trace route assignment. You know, this is, you're trying to understand how packet will actually arrive at its destination. Okay. Now, how is it actually going to determine? All right, how are these package exchanges going to be able to determine which um, um, which other package exchange service it should actually send the data to? Well, obviously, this um, can depend from network to network. All right. Notice that usually routers would have multiple output queues, all right, in order to be able to send to different locations. And and each router might adopt different strategies, all right. So you might use, for example, what is known as a hot potato strategy, where essentially you would look at the queues that you have available and you'd say, all right, which queue is least used currently? And you'd say it's this one, all right, it's queue number 1. So you'd say, all right, this packet is going to go into queue number 1, all right. So you literally look for the shortest queue and you would say, all right, I'm going to add you to that queue. And you'll be off to a particular destination. And then it's somebody else's problem, essentially. Another strategy would be where the packet itself, all right, would have a predetermined route, all right, embedded in it. So essentially, you would tell it, listen, I want to pass through these particular nodes, all right? In which case, the router will just literally pass it along, all right, those particular routes, all right? Essentially, it will be following the instructions that are embedded onto the packet. This particular strategy is quite fast for the simple reason that you would know, all right, um, uh, what you would need to do, as in the packet itself is telling you what it needs from that particular router. All right. Another way, all right, of doing it would be through the use of having some form of directory. It's known as directory routing. Essentially, the router would have what is known as a routing table. All right. And essentially, it would identify what would be the best way to transfer a particular packet to a particular destination via these routing tables. It will look it up, it will reference an adequate output queue, and it would place it within that output queue. These are different techniques that are used within different routers, essentially. All right. Now, what are the main advantages of packet switching? As I said, all right, before, the main advantage is that we're making use of our lines more so than one would have within circuit switching, as we can actually send multiple packets over the same line from multiple different communications. All right, so packets can be transmitted as fast as possible. The data rate, all right, um, can also vary because the speed of each and every node can work at its own rate. All right. Notice that each node can have what are known as buffers that will be able to receive, all right, packets and deal with them in the rate that they would be able to deal with them. So essentially, you wouldn't lose many packets. You can lose packets like that, but you wouldn't lose as many. All right. Also, packets, all right, would be accepted even if, all right, the system or the node itself is quite slow. All right. You might slow down delivery, yes, but at least packets won't be lost to the ether, essentially. All right. Although you could also have implementations of priorities in order to fast track certain packets as opposed to others. However, one of the main things that you can also think about with regards to packet switching is that essentially it maximizes your network connections because not only is it more efficient, it's also cheaper. However, it could also be slightly slower. If you think about it, it's like saying, listen, if I had a direct or private road from where I live to where I work, you are always going to arrive at the same amount of time. Why? Because you're never going to find any traffic because that road is yours. All right. If you're using a shared road, okay, then you might get block cogged down or blocked down with congestion, just like packets. Essentially, it's a very very similar. All right. However, with packet switching, it's also cheaper to have um, uh, public roads rather than having private roads because it also provides alternatives. All right. If in this fictitious idea, I have a private road that takes me from home to work, all right, and nobody else is allowed to use it. If that connection fails, then I don't have any other alternatives. All right. With packet switching or the public road, for example, if one road is blocked, then there should be another one available, unless Ian Borsch decides to dig up that road as well, and then dig up the other one, and then dig up the next one, and so on and so forth. Anyway, small joke. um, However, circuit switching, on the other hand, is more ideal, all right, if you want to make use of real-time transmission, all right. So an example of a circuit switching type environment would be, for example, what one might expect with regards to a cable connection. All right, if you have a connection with Marita, for example, all right, in your home, all right. I don't know if you've ever experienced this. Let's say you had a fault in your line, all right, and your internet went down. All right. Have you ever tried to reestablish your connection? All right. It usually takes some time before it actually establishes its connection. That is because essentially underneath you would actually be using circuit switching in order to connect to um, uh, your service provider. All right, and then um, uh, your service provider, once it establishes the connection, then you would actually have um, uh, it is quite transparent. All right, but other than that, typical, um, uh, it can take a while in order to establish. But in that instance, then you're using um, uh, a connection which is probably dedicated to you. All right, at that particular point in time. Any questions so far, guys? I don't know if you're trying to say something, Floyd,
All
but
good. No, it was my mic was muted. All good, thank you.
all right.
I'm okay, thank you.
All right. Okay. Cool.
I'm okay.
Right. So essentially, the important thing that we need to understand with regards to packet switching is that essentially each station, all right, so the computer who's about to send the information or long messages will break down that message into packets. Those packets are sent one at a time over the network. The packets are passed through the network either as datagrams, which would be able to traverse the network in different, taking different paths in order to reach its destination, or as packets can be handled in what is known as a virtual circuit. All right, as we were sort of like, as I was sort of like alluding to, the idea of a datagram packet is a packet which is using a connectionless packet switching, meaning that a packet can literally take any route, all right, from source to destination, all right. They might arrive out of order, they might go missing, they might, and then the receiver would need to reorder the packets and ask for retransmission of missing packets in order to reassemble the data. However, with a virtual circuit, essentially what would happen is that you would essentially you predetermine where the packets would need to pass through using a pre-planned route, all right, and the packet will be sent along that route in order to establish the communication. The good thing about this is that each packet, all right, um, uh, would be able to um, contain, all right, this predefined route in of itself, therefore making it easier for the routing to happen. However, it would also require some form of establishment of a connection between the the source and the destination, essentially. All right. Um, uh, so it is kind of like establishing a uh, a, uh, a circuit between the two source and destination. All right, for the communication to happen. notice that you are still making use of the advantages of packet switching in the sense that that same route can be used by other communications. All right, so it's not a dedicated path essentially. All right. However, virtual circuits can actually receive data in order since you're sending packets in order, all right, one at a time, all right, then across that circuit or that virtual circuit, you will be receiving the packets in order as well, all right. So in this case, all right, you would be receiving packets, all right, um, more quickly because no routing decisions need to be made. However, it is less reliable. Why is it less reliable? It's less reliable because if some form of collision happens between one packet and another and that packet is lost, all right, then or let's say that a packet passes through a node and the node loses its connections for want of another word, then essentially that virtual circuit is no longer a viable path. It's no longer a viable path from the source to the destination. So essentially, in that case, you would need to re-establish a new connection in that case. All right. Probably you have experienced this in the past whereby you try to log into a particular service and for some reason or another the connection cuts out and then you would need to re-establish your connection before you will be able to start up that service. Essentially, this is what we're talking about here as well. Okay. So if one of the nodes of the virtual circuit goes offline for some reason or another, then that route is no longer a viable route. Okay. Whereas with the datagram approach, all right, there's no setup required. Because you don't have to set up the connection, all right, and it's much better if you're just sending a few packets, all right. It's more flexible, all right, because obviously if one node within the network goes down, all right, then you will be able to make use of other routes, all right, in order to reach your destination. Okay, any questions so far?
Yes, more on what you said about the packets. When you say packets collide,
Yes.
I think it was shown in the video initially as well, the
Yes.
one you told us to. Did they actually collide? Or maybe they
Mana.
get lost? What actually happens under the hood?
Mana, what happens under the hood? So what might happen is that you might have certain bits going one way on a wire or on a transmission medium, and you have certain bits going the other way. Literally, they collide. Um, uh, Imagine, think of them as voltages along a piece of wire. You know, so if over here I'm trying to send data from this source to this destination 1010, for example, and over here I'm sending 1001, for example, and they're going in opposite directions, they might corrupt the data, so essentially it becomes a collision.
All right.
All right, that
Wait.
is a very
Close
very
as we can get.
yes. You're not going to actually see collision, but packets get lost essentially. All right, because two packets might have collided with each other in that sense. All right, as they interfere with each other. Okay.
Thank you.
All right. So, what about message switching? So message switching is yet another type of switching, whereby the message that is actually being transferred from one source to the other across these nodes needs to be sent in its entirety from node to node until it reaches its destination. Essentially, what this means is that each node will need to be able to first receive the entire message before forwarding it off to the next node. All right. So essentially, what this means is when it comes to larger um, uh, pieces of data that are actually going to be transmitted from one location to the next, these facilities would actually require large or vast areas of storage in order to be able to accumulate all of the data before they can actually send it over to somewhere else. All right. Obviously, you would also need to have some form of intelligence in order to determine when exchange can actually be made and when it can actually be forwarded. All right. And you need to have more processing time in order to be able to handle and accumulate all of the data before you can actually send the message. All right. The good thing about message switching is that it gives greater confidence that the message has actually arrived complete. All right. So that is one reason why one would actually make use of message switching. All right, so that sort of like encompasses the different types of switching that we're going to be talking that you need to know about for this course. What we're now going to start discussing is the idea of the layered architecture. All right. Now, the objective behind these sets of slides is in order to understand how data, all right, is actually encompassed as a packet and then sent and then received on the other end. Okay, essentially, this layered architecture allows for all of the different types of communication that we have over the internet and that we experience over the internet. So essentially, this layered architecture allows us to create a complex structure, all right, using a particular framework in order to be able to allow us to transmit data. Essentially, um, uh, we have a network architecture, all right, which is structured using multiple layers, all right, each of which using different protocols, all right, that allows our networks, all right, to be designed and implemented so that we will be able to establish communications um, between these different devices communicated over the internet. Essentially, we're going to be making use of computer and network architectures, which would have a defined hierarchy of these levels, where each of these levels is going to perform a particular function, all right, that is going to be implemented separately. However, each function is going to feed into the next layer. And there's going to be a sort of like interface, all right, or a protocol as to how one layer is going to communicate with another layer, all right. In fact, the higher levels are going to um, call upon the services of lower levels in order to read, all right, whereas the higher levels are also going to be providing data to the lower levels when you're sending. Let me explain this using a little bit of an analogy. All right. So let's say I want to send a letter, all right, to a friend of mine. Okay. What do I need to do? So, first and foremost, I need to take a piece of paper and write the letter, all right, with my data. That is the data that I'm going to be sending. All right. I would then need to take my data, all right, my letter, and place it inside an envelope. All right. Then that envelope needs to be placed inside of a letterbox. All right. The letterbox then needs to be opened by the post officer, all right, and take that letter to the post office. The post office then sorts it, all right, so that it knows where it needs to go, and then it's transported to a different destination post office. Once it reaches that destination post office, then what needs to happen is that it needs to be delivered to the destination. All right. Once the letter has been delivered at the destination, the receiver needs to open the letter. All right, and read the content. So as you can see, with this analogy of sending and receiving a letter, there are a number of stages which are sort of like similar but opposite on both sides. So on the higher level, all right, if I am writing a letter and putting it into an envelope, all right, from the sender's point of view, then the receiver will need to take the letter, open it, and then read the letter. So notice that they are relatively at the same level. If I am delivering it to a letterbox, all right, so that it can be taken by the post office also is going to is going to have to deliver to the destination mailbox. All right, so that is a middle layer, if you will. All right, the lower layer is essentially the sorting. All right, from the sender's point of view at the post office, taking it to the destination post office. All right, so as you can see, there are a number of different tiers, if you will, of steps that needs to happen on, but opposite for the same communication in order to happen. Do you understand this principle? Are there any questions, guys?
Understood, sir. It's
All right.
understood. It's understood. Thank
Okay.
you, sir.
So, in a very similar fashion, all right, when we want to send data on a computer, all right, between two computers, all right, we need to do similar processes in order um, to to transfer the data that we need to transfer. Notice that the layers themselves, so at a specific layer, all right, we from the point of we're going to have an implementation, all right, from the sender's perspective, and we're going to have an implementation, all right, from the receiver's perspective. So one is actually making it easier or making it available in order to be able to transmit. The other is actually trying to read it. They are literally two sides of the same coin. On the same level, essentially, we call that level, all right, layers on the same level as being peers, all right? They communicate using a set of rules to other layers, all right? Or they receive information from other layers using certain rules, all right? And these rules are defined through what is known as a protocol stack. So the way that one layer communicates with the next layer, and which communicates with the next layer, and which communicates with the next layer, is following a certain protocol. All right. So, in a very similar fashion, all right, computer A will need to pass data by taking it from layer 3 down to layer 2 down to layer 1 and passing it over, all right, over physical communication to computer B, all right, which needs to unpack itself by passing through layer 1 through to layer 2 through to layer 3 respectively. Notice that layer 3 for computer A and computer B are known as peers, layer 2 for computer A and computer B are known as peers, and so on and so forth. All right. So this is a simplification of what happens when we're actually communicating between two computers. All right. So what are the properties of this layered architecture. First and foremost, each and every layer has their own function. They are functionally independent of the next layer. All right. However, they know what they need to feed into the next layer. All right. So there is a predefined and well-defined interface. The cool thing about this is that if we want to, all right, we can re-implement or or replace a layer, all right, implementation with another layer implementation. As long as it fits the same interface, everything should work well. This is why it is possible for one to actually have different routers and different network devices and different computers, all from different manufacturers, communicating all together on the same network. All right, because they all address each and every one of these layers. They might address it internally differently, all right, but the output is the same. It's kind of like if you get yourself in a car, all right, and you feel the pedals, all right, you're always going to have a gas pedal and you're going to have a brake pedal, no matter what kind of engine you have under the hood. All right, so you would imagine that the gas pedal is going to make your car go faster and the brake pedal to make your car go slower. All right, now obviously that would depend entirely how it's going to make it go faster or how it's going to make it go slower. It depends entirely upon how it's actually implemented under the hood. So if you have a petrol car, it might do it in one way. If you have a diesel car, it will do it another way. If you have an electric car, it's going to do it another way. If you have a hybrid car, it's going to be doing it in a different way altogether, and so on and so forth. However, the end result is going to be the same. All right, which is going to be more efficient than the other? Well, that is not really that important for us in this particular stage. All right. What we're saying is that we know what each layer needs as an input and how it needs to output it, how it's going to do, how it's going to transform the input into the output. All right. That is not of a concern to us. All right. That is why they are interchangeable. All right. Obviously, with newer or more modern versions that work on that particular layer. All right. They obviously are communicating indirectly with their opposite peer on their counterpart. All right. So essentially, a layer in a specific um, uh, level in the hierarchy on one side is communicating directly or directly, sorry, with its peer on the counterpart from the receiver. All right. So the sender is communicating with the receiver. All right. And when when you have a sender, when sending packets, the layer on top is sending data to the layer at the bottom, and the opposite is happening, all right, when you're receiving. So the bottom layer feeds in to the top to the layer above that. That is then read by the layer on top of that, and so on and so forth. All right. So what are the main advantages of this type of architecture? Well, first and foremost, it divides up the complex operation of sending data from one device to another into smaller, easier to implement, and easier to test sections. All right. As we mentioned before, I can literally replace one version of the layer with yet another version of that same layer. As long as they fit the same protocol, as long as they fit the same form of communication, then my system should still work. It's kind of like, if you will, if I had to take out a graphic card on my motherboard and plonk in yet a newer graphic card, All right, as long as they're using the same interface, I am able to do that. The same thing can happen with a CPU. The same thing can happen because they're working with the same interface. All right, same thing can happen with these algorithms essentially, because a protocol is nothing but an algorithm. All right, and as we said, it also provides us with the ability to be able to use different devices made by completely and different manufacturers in order to communicate with each other, all right, because they're making use of this standardized architecture. Okay. In fact, what we're going to be talking about, all right, in our case, is we're going to be talking about two main models, all right? We're going to be talking about the OSI model, or the OSI reference model, or the Open System Interconnection model, all right? And then we're going to be looking at the more, um, uh, the which is more, so the OSI model is um, uh, more of a theoretical model, if you will, whereas the internet model, on the other hand, is more of a practical model. Okay. Um, so we're going to be looking at how these layers are actually structured and what each layer actually does and how communication happens from one device to the other. All right. So before we actually look at the OSI or TCP/IP and what have you, what happened before then? Well, essentially, prior to the OSI model coming out, all right. So we're talking 1980s here, all right, or even before then. Whenever we had devices communicated with one another, all right, they were literally vendor-specific models of communication. So, for example, if you had an IBM system. You would need to be able to communicate with only other IBM systems because only IBM systems made use of this um, uh, communication protocol. All right. However, as computers became more and more diverse and they became more and more available worldwide, right? Remember in the 1980s, computers were still, even in the 70s and 80s, computers were relatively um, uh, were not as popular as they are nowadays. All right, but with the growing desire for one to use computers and for the growing number of vendors that you actually had and the growing number of desire for compatibility between different devices, all right, a necessity grew, all right, for one to have a vendor a vendor neutral networking model. Essentially, the idea, all right, to come up with a standard so that every form of network device would be able to communicate with each other, thus aiding um, uh, in competition. All right, because at the end of the day, if you are compatible, all right, with other devices, then you're going to be obviously going to be more desirable as a device, all right, and it's also going to reduce complexity when it comes to configuring your computer systems, all right. And this is where the OSI model came in, all right. So the OSI uh, model, all right, is was developed by the ISO, um, so the International Organization for Standardization, all right, and it created this model by the late 1970s. The idea was in order to standardize the way data, networking, and protocols allowed communication between computers across the globe. All right. Now, from that, all right, from the OSI model, um, was spawned the internet model, or what we commonly refer to as the TCP/IP model. The internet model was a more down-to-earth approach, all right, of the OSI model, which was first developed by the Department of Defense, which eventually then became what we know as the TCP/IP model that we use today. All right. So essentially, by the 1990s, all right, we were adapting all of our systems to make use of the TCP/IP model that overtook the OSI model. In which case, all right, the OSI model now is more of a theoretical model that covers basically every aspect in detail, whereas the TCP/IP model is less formal and less complex to develop, all right, because it's not so detailed. And today, we really and truly make use of a hybrid between the two, all right. So the OSI model is made up of 7 different layers, all right. So you have the application layer, the presentation layer, the session layer, the transport layer, the network layer, the data link layer, and the physical layer. The internet model, all right, or the TCP/IP model has what is known as the application layer, the transport layer, the internet layer, and the network access layer. And the hybrid model that we use nowadays has the application, transport, network, data link, and the physical layer. Notice, all right, that the internet model, all right, the internet model's application layer, all right, is the same as having the application, presentation, and session layer all combined into one. All right. The internet layer of the internet model is essentially identical to the network layer of the OSI model. All right. However, the network access layer that we have within the internet model is identical to the data link and the physical layer combined together. Same can be applied for the hybrid model. The hybrid model, um, essentially, the only difference between the hybrid model and the internet model is that it fragments this network access layer to be more similar to the OSI model. However, it does combine the application, presentation, and sessions of the OSI model into one application layer over here. Is this clear so far, guys?
Yeah, it's all clear from my end.
Okay. Any questions? Okay. So, so let's take a little bit of a look at these layers in a little bit more detail. All right. So, essentially, this is essentially what I was explaining earlier. All right. So in the internet model developed by the Department of Defense, all right, the application, presentation, and session layer became one application layer. Transport layer remained the same. Network and internet layer remained the same, and the data link and physical layer got combined into the network access layer for the Department of Defense model. All right. Remember that each and every one of these layers, all right, are hosted on a protocol stack. All right. So if host 1 is trying to communicate with host 2, all right, it will go from layer 5 to layer 4 to layer 3 to layer 2 to layer 1, communicate over a physical medium, and then host 2 needs to go from layer 1 to layer 2 to layer 3 to layer 4 to layer 5 in order to be able to read back the message that was sent by host 1. All right, notice that each layer, all right, is from on the host, on each host is known as a peer. All right, a peer layer. So essentially, these layering systems allows for peer-to-peer conversations in order to happen. As we said, it reduced complexity, all right, and it allowed layers to offer services to layers above it, all right, and it also allowed layers to shield unnecessary information from for lower layers, all right, by abstracting away or hiding or encapsulating what has been done before. So essentially, what we're saying is that every layer, so what was going on in layer 5 is going to be hidden from what is being done within level 4, which is going to be hidden what is going to be done from layer 3, and so on and so forth. Essentially, what is really important is that the interface between one layer and the next remains the same. That's the important part. Okay, kind of like how um, if you want to upgrade your graphic card, you need to make use of the same PCI Express slot, right? If you take out one graphic card and slot in a new one, all right, as long as it fits on the same PCI Express slot, you would have changed the graphic card and your computer would still work, all right, in a very similar fashion that we have over here, okay? But the processes that are going on in each layer is going to be abstracted away from each and every other layer that is going to be following it, essentially, okay? Um, uh, so, um, uh, So essentially, every layer in of itself is both offering a service, all right, as well as following a protocol. What do we mean by this? So every layer is offering a service because each layer provides a service to the layer above it. All right. So in order for whoops, in order for layer 5 to be able to read information, all right, it needs to be serviced by layer 4. For layer 4 to be able to do something, it needs to be serviced by layer 3, and so on and so forth. However, each layer, all right, is in then following a number, all right, of rules in order to convert it yet again for the next layer, all right. Essentially, the protocol aspect of the layer is that each layer needs to follow a certain set of rules governing how the data needs to be processed, all right, so that the next layer will be able to take on the baton as it will in the data communication relay race, if you will, all right. Now, there are a number of design issues that one needs to take into consideration when coming up with these layers. The first issue that we need to address is addressing. Essentially, when we talk about addressing, we're talking about how we're going to be able to identify, all right, the source and the destination nodes. All right, this is important. All right, uh, because um, uh, it is um, uh, it is going to be it's going to be fundamental, all right, in order to be able to establish a successful communication between one host and the other, all right. Um, uh, so it will also allow us to be able to take that data from the source to its final destination. We also need to take into consideration some form of error control. Essentially, um, we need to be able, all right, to ensure that messages are arriving at their destination correctly, all right, in spite of imperfections maybe in the physical medium that we're actually traversing, all right, in spite of interference that we might have in the mediums that we're using, and so on and so forth. So we need to make sure that our message is arriving intact. We also need to ensure that our that our system has some form of flow control. It is impossible. It is pointless having a fast sender, all right, swamping a slow receiver, right? Because a slow receiver is not going to act any faster the more signals you're actually sending it. So you need to have some form of control, which is actually going to moderate or modulate the amount of data and the amount of speed that you're actually going to have within that communication. So essentially, your flow is going to be as fast as your slowest um, uh, receiver on your communication chain. You're also going to need to be able to perform what is known as multiplexing. Multiplexing is essentially the ability to make maximum utilization of the communication medium, all right, by supporting many simultaneous forms of communication at the same time, all right? So you can have multiple unrelated conversations happening over the same medium at the same time, thus making the best use of that particular medium. And finally, we also need to address the issue of routing, i.e., we need to be able to find the path, all right, for our packets from the source to the destination, all right, which might take multiple paths in order for it to actually reach its destination. All right. So these are the different issues that the design of the layers is seeking to address. All right. So essentially, each as we said, each layer is going to be communicating directly with the layer beneath it or the layer above it. All right. And if we're sending, data is going to be flowing down the layers. If we're receiving, data is going to be flowing up the layers. And in order to be able to send data, all right, what we're going to be doing is we're taking our data and we're enveloping it, all right, so we're placing it within a container, if you will, all right, through the use of headers and sometimes tailors, all right, on the piece of information that is arriving at each and every level, all right. If we are sending data, we are encapsulating this data that we are receiving from previous layers with more and more envelopes, adding more and more information that is actually necessary in order to deliver that packet across the medium. On the other hand, if we are receiving this datum, all right, or this packet, then essentially the protocol works in the inverse. Essentially, what we do is we strip away these envelopes, these headers, and these tailors, all right, until we eventually reach back to the original data which we want to read in the first place. All right. So essentially, this is what happens. All right. When we're sending a message, all right, so we have our outgoing message, and here's when we have our incoming message. So essentially, this is our sender over here, and this is our receiver. So let's say that we have an application that wants to send data, all right, to another receiver. So we'll have our data units, all right, the data that we're going to be storing within the packet, which goes through the first layer, which is the application layer. Since we're sending that data, we're going to attach or append, if you will, an application layer header to the data unit, all right? And we pass it on to the presentation layer. The presentation layer is going to take that data, including the application layer header, and it's also going to encapsulate its own presentation header to that. And then it's going to pass it on to the session layer. All right, as you can see, the session layer then appends, all right, its own session header as well, and then transfers the data onto the transport layer. The transport layer introduces its own transport header. All right, and once it does that, it moves it onto the network layer. All right, the network layer applies its own network header. All right, and applies it down to the physical, to the data link layer. The data link layer, and then encapsulates the data with a data link header followed by a data link footer. All right, and then passes it down to the physical layer. The physical layer then sends this data across the physical connection medium, be it wired connection, Wi-Fi, what have you. All right, this doesn't really matter. All right, it sends it as voltages or I don't know, lights or whatever. All right, or radio waves until it reaches the destination. Those are converted back into bits. All right, which gives us back the data from the data link layer. The data link layer will strip away, all right, um, from the receiver's point of view, will strip away the header and the footer from the data link layer that we received from the host. That in turn is fed back into the network layer, which in turn strips away the network header. All right, that was given to us by the the sender, and then as you can see, each and every one of these headers is then stripped away until eventually we reach back up to the application layer. All right, which will allow us to be able to read the data back from the receiver's point of view. So as you can see, each layer is going to be encapsulating, all right, the data units that it's receiving from the previous layer, all right, upon sending, and then removing them or de-encapsulating, all right, so that it can actually send it all the way back up in order to be able to read this information. Notice, guys, that this diagram is incredibly important. Take the hint, all right? You might be asked to reproduce this diagram, all right, during an examination session, all right? It's not outside of the realms of possibility. Hint, hint, wink, wink, nudge, nudge, holla, holla, take the hint. All right? Is this understood, guys?
Yes, sir.
Yes?
Yep. Thank you.
Okay. So, um, how are you going to remember these 7 different layers? Here are some acronyms that can actually help you do so. All right, you can use please do not throw away, do not throw sausage pizza away. All right, P for physical, D for data link, N for network, T for transport, S for session, P for presentation, and A for application layer. All right, you have acronyms going one way and acronyms going the other way, whichever floats your boat. All right, this is just a study technique which will help you. All right, help you remember this the order of these layers because this is very, 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 very important. Okay, right. So, were you going to ask something, Bridget? Okay. Okay. Fair enough. Right. So when we take a look at these these layers, all right, these 7 layers. Essentially, we can split these layers into 2 sections, all right. The first 3, all right, so the application, presentation, and the session layer, those are known as the application set layers, all right. Whereas the transport, network, data, and physical layer are what are known as the transportation set layers. Essentially, the first 3 are um, uh, are pretty much used in order um, uh, to define how data is actually going to be transmitted. All right, that is going to be legible and understandable by the end application on the receiver end. Whereas the transport set, right, these last 4, all right, the 4 at the bottom, essentially are really and truly focused primarily on how you're actually going to transmit the data across the network. So let's try to take a little bit of an understanding of what each and every one of these layers actually does. All right. So the first layer that we're going to be talking about is the application layer, the one at the very top. All right. This layer, all right, of the OSI model is the closest layer that you have to the end user, by which we mean that this is the layer that your applications are going to be predominantly um, communicating with, all right, when you're going to be sending information to another computer, all right, over a network, all right. Essentially, this layer's responsibility is to interact with the software application and implement a form of um, communication communication system, all right, that that particular application can have with any form of um, signal that it wants to send out and it is going to receive, all right. um, so essentially the applications layer's functionality, all right, is typically to identify, all right, um, who you can actually communicate with, what kind of resources are available, and also to synchronize your communications. Essentially, this layer is going to determine also what kind of communication you're actually going to have. So if your application happens to be, for instance, a web browser, all right, then it's going to make use of protocols such as the HTTP protocol, all right, for the hypertext transfer protocol. If it is going to be a file server, all right, if your application is a file server, then it might have the file transfer protocol. If it's an email application, then it might be making use of the POP or the SMTP protocols. All right. So essentially, this is what the application layer is primarily focused on. All right, providing um, uh, who you're going to be communicating with, what resources are going to be available, and synchronizing the communication that is going to happen across those peers. The presentation level, all right, that is responsible primarily of formatting the data that you're actually going to be sending in a format that is actually going to be understood, all right, by the receivers and or vice versa, all right. It is going to be responsible for taking the data and representing it in a particular way that is going to be understood in the application layer. All right, depending obviously if we're talking about you being on the sender side or you being on the receiver side. All right, an example of this might be to take, for example, text and then coding it in ASCII format or converting it from ASCII to Unicode, or from ASCII to EBC DIC coding. All right, so it doesn't really matter. It essentially is doing the translations for you. Essentially, this layer. All right, and essentially what also sometimes happens in this layer also, it could also have a level of encryption, although it can be done in other layers as well, such as the application, session, transport, or network layers. And it can also take care of, say, something like data compression, all right, as well. Okay, so obviously, if you're sending, it's compressing data. If you're receiving, you are decompressing data. If you're sending encrypted data, all right, and it's encrypting, all right, you're encrypting upon sending, and you're decrypting when you're receiving. All right, obviously, remember that they have sort of like a dual purpose. Okay, the session layer. All right, the session layer is predominantly focused on establishing um, a mechanism for opening a connection and then closing a connection. All right, during at the ends, if you will, of um, of your communication. Essentially, it is managing the session of communication that you have between sender and receiver, essentially. All right. It allows for the, the the data stream, all right, to be created, all right, maintained, and then destroyed, all right. Obviously, it might also need to make sure that, for example, certain data would be synchronized, for example. All right. So if we had to take, for instance, this video call, you would want, for example, the video that you're watching, all right, would match the audio that is coming in, so that my lip movements and the video and the audio that you might be receiving would arrive at the same time, so that you would have lip synced video, all right, essentially. So essentially, what this layer is trying to do is it's trying to make sure that you have authentication, all right, upon establishing the connection, all right. It will also determine what your permissions are actually going to be. It's going to be what is going to re-establish a connection if a connection is lost, for example, and it's also going to determine the type of communication that you're going to have. That you're going to have. Are you going to have two-way communication? Are you going to have one way versus one way at a time communication, or half full duplex, half duplex? All right. Are you going to have only one way communication, being simplex? All right. So this is what the session layer's job is all about. All right. The transport layer, on the other hand, all right, is what really provides end-to-end communication, all right, services for applications. What does this mean? It means that this layer is what is really and truly making sure that you're going to have a connected, all right, data stream, all right. So essentially, um, it is going to be in charge of taking your data and dividing them into packets, all right, so that they can actually be sent, all right, down to the sender. Obviously, the packets would need to be reassembled from the other end. So when we're talking about segmenting data, we're also talking about desegmenting data as well. It's also going to be in charge of creating the sequence for the packets. It's also going to be able to introduce an element of reliability such that, for example, when we're using something like the TCP/IP network, the TCP/IP communication system, you would be able to um, say whether or not a packet has arrived or not, all right, by sending an acknowledgement, all right, back to the sender saying, listen, yes, I've received that particular packet, or rather, you can send also um, an, a non acknowledgement, basically saying that you haven't received a particular package after a packet after an amount of time, all right, so therefore you would be able to have a reliable data stream, all right, and it can also be used, this transport layer, in order to try to alleviate congestion within the telecommunications network. How does it do that? It does that by controlling how traffic actually enters the telecommunication network. All right, thus reducing the chance of congestion. The network layer, on the other hand, all right, is responsible for routing packets, all right, to intermediate routers. And so, in fact, this layer is what is used predominantly by routers, all right, which are connected to yet other routers, all right. Essentially, yes. Was there a question? Apparently not. Okay. Um, the network layer, as I was saying, is predominantly the layer that is used by routers in order to be able to identify where the packet needs to go to next, essentially for routing purposes. Essentially, this network layer is primarily focused around routing those packets. It's also in charge of reporting delivery failures. All right. So let's say, for instance, that a packet um, uh, is has is not going to arrive at its destination. It can automatically send a signal back, all right, to the sender saying, listen, that packet is not going to arrive yet, or it has timed out, please send another one, all right. So it doesn't necessarily have to arrive from the receiver. It can also arrive from the network layer. So essentially, every packet has what is known as a time to live. All right, it is an amount of time, or a number of hops, if you will, that a packet will continue to live on the network. All right, if that packet um, um, does a number of hops and it expires, all right, then essentially it's going to be destroyed, and the router can automatically tell whether or not a packet is actually going to reach its destination or not. So in that case, it will be able to report a delivery failure. All right, and um, another thing that the network can also do is that it can also support logical addressing. What do we mean by this? So, take for instance your home network. All right. Um, if you have more than one computer or one device connected in your home, all right, you're probably going to have some form of router in your home. All right. Um, uh, if you look at the IP address of your device, all right, connected to your network, all right, to your router, that IP address is going to be completely different from the IP address that is actually going to be provided to you by your internet service provider. why is this the case? Well, what your router is doing is it's providing sort of like a logical address for your device on that particular network. All right. However, communication is happening over the other IP address that is provided to you by the ISP. In fact, as you're going to be seeing when you're going to be doing your assignment, you're going to realize that your IP address is going to be completely different from the IP address that you're using internally in your home network. So that is what we know as logical addressing. All right. The data link layer, all right, the data link layer is the layer that is predominantly focused on uh, transferring data between network entities. This is the layer that most switches tend to use to operate in. So notice switch is sort of like a step down from a router. All right, the router is a more of an expensive device than the switch. The switch um, focuses primarily its communications over the physical layer, and the physical layer is primarily focused on um, detecting the possibility of errors that may occur, all right, from data that it's receiving, all right, from the physical layer as well. So essentially, it's predominantly this layer is predominantly concerned on the delivery of certain frames of data on the same network and detecting errors, all right, that is coming in, all right, from the physical layer, essentially. All right. In fact, when we attempt to use a medium at the same time, all right, we might get a collision. This is where the data link layer comes in, as it will detect frame collisions, all right, and it will try to recover from those frame collisions in order to make sure that um, they are either reduced, all right, um, or um, or prevent them entirely, essentially. All right. So this is where the collision comes in. Maybe answering the question that you had earlier with regards to how collisions occur. Really and truly, it's when a medium is being used simultaneously, as we had discussed earlier. So, how does it? How does this data link layer work? All right. So, how the what functions does it provide, and how does it provide those services? So, first and foremost, the data link layer, as we mentioned, is tasked with trying to have reliable data transfer on your local network. All right. And how does it do that? It essentially sends blocks of data, your data frames, with necessary synchronization, bit error, so that you can detect whether or not you actually have had alterations or error correction within the data, as well as flow control. Essentially, the way that it does that is that it makes use of the MAC addresses of the device connected to the physical um, um, network. All right, in order to identify the different devices that happen to be on that particular system. And then what it also provides is that it also provides an element of buffering in order to be able to help packets arrive at certain receivers, all right, in a rate that they can actually consume, all right, especially if you have devices which are slower than other devices. Essentially, we don't want to flood those devices too much when you are sending these packets. All right. Finally, all right, and we'll talk about this, and then we'll stop here for today. We'll talk about the physical layer. The physical layer essentially is the layer that is predominantly focused on how to actually physically send the data signals across the device. So notice that the physical layer can be can be the layer that is going to determine how data is actually going to be sent across the medium that you're currently using. Now, the different mediums can be using different types of technology. So you can have a copper wire, for example, in order to transmit data, in which case you would be playing around with voltages. You could be using optical media, in which case you'll be using different light sources in our flashes of light in order to send your data down that cable. You might be using Wi-Fi, in which case the physical layer is actually going to be sending physical waves to to the next node, and so on and so forth. So essentially, the physical layer is essentially um, um, tasked with the the translation of the data that actually needs to be sent to the actual ones and zeros, or the representations of the ones and zeros on the physical medium that you're actually communicating with on that particular network. All right, that is essentially what the physical layer's job is all about. All right. Um, so obviously you would what this means, it means that you would need to perform modulation or conversion of the ones and zeros that you have on your computer into those signals that needs to be sent across that signal. It needs to control voltages. It needs to make sure that you have that you're timing your signals in order to be able to send that signal. All right, and you also needs to be able. It also needs to be able to establish connections with your medium. So I have a question regarding the exam at the end of the scholastic year. There are two different versions. Do we need to apply for one version, or depending on whether we're doing the diploma or degree? Let me just see the this is from an email. Am I?
Yes, the registrar sent that to us a little while ago, but I'm not sure. Are there two different versions, or is it just everyone gets the same exam?
No, please note that examinations for part-time students attending University of London exams in May and June are normally scheduled in the evening during the respective lecture. But now, this is for University of London's. The first part that you highlighted is for the University of London students. If you are following a University of London course, um, uh, uh, essentially you need to be aware that you have examinations in May, June. All right. Um, uh, which are usually held in the evenings. All right. However, part-time students who wish to sit for any of the scheduled exams with the full-time students may do so by essentially. Um, uh, so, are you doing a University of London program?
Well, I thought it was that we all do the diploma, and then afterwards we have the choice whether to continue to for a degree. I didn't know we have to make that decision now, do we?
But Mana, so what you're doing, you're currently doing the St. Martin's diploma, which is going to be then used as your entry point into the degree with the University of London, if that is the case. You're doing, aren't you doing the
Well,
diploma?
I was
in
originally I
games?
was going for the degree, but I didn't. So there are two different exams, and we need to make sure we are doing the right one when it comes to the summer. I thought there was just one exam for everyone.
No, Mana. If you are, first and foremost, I would. First and foremost, I would. It depends on what program you have registered for. All right. So so I would suggest that if you have any queries, you would contact the registrar first and foremost. Secondly, the I was under the impression that you personally, Bridget, you were currently doing the diploma in games with St. Martin's. Yes, 'Cause last year
I
I
thought
thought.
I was set up for the degree.
Yes, yes,
I-
but the degree comes into play as of your second year.
Okay.
So
So do-
essentially, you would be doing your diploma with us, which for the University of London acts as sort of like a prerequisite, all right,
Mhm.
for their degree, and they also forego the requirements that you would actually do their first year.
Okay. Because
You
so
want
when you say second year, do you mean third year for full-time students or for
Mana,
third time?
usually Mana.
Because this is my
Say,
second year.
yes, yes. Granted. Usually for full-time students, it's 3 years. That's why I go first year, second year, third year. All right. In my eyes, you're still first year students. All
Okay.
right, because you're currently still doing the diploma. All right. So essentially, we have let's call them level 1, level 2, level 3. Okay, to make it easier. Okay. You're currently in level 1. You're doing level 1 with St. Martin's, which in turn is going to be used as your entry requirement, but also continuation with the University of London.
Okay, so this summer we will all be doing the same exam. We don't have to worry about this yet.
If in your in I cannot say everybody, but in your case,
Mm-hmm.
I would imagine that is the case. Last year you didn't have to sit for St. Martin's examinations and University of London examinations. No,
No.
so that is going to be the same case this year
Okay. All right. Thank you for
for
explaining.
for you. All right.
Mhm.
I wouldn't. I'm not going to be presumptuous enough in order to say that is going to be the case for everybody. All right. So that's just to be clear. All right.
Okay. Thank
Obviously,
you.
if you
Sorry for
have
the interruption.
But if you have questions or queries, please do make sure that you contact the registrar and clarify these issues. All right, just to
All
make sure
right.
that what you need to do, because I wouldn't know exactly what courses you have registered for. To and what obligations you actually have per student. All right. So that is essentially all I can do from my end. All right.
All right. Thank you.
All right.
Thanks.
Right. Okay. So I'm going to stop here for today. All right. I don't know if you have any other questions with regards to the topics that we have just discussed up to this point.
Yes, just the one.
Yes.
On the network layer, right? You said that there was a limited number of hops a packet can do.
It basically what I was saying is that a packet would have a predetermined number of hops that it can do before it dies. All right. The reason is so that if packets never reach their destination,
They can be timed out.
they would be timed out, and therefore they would be able to be destroyed essentially, and therefore not
Alright.
clog up the rest of the network.
Okay, so it's the usual timeout issue as opposed
Yes,
to having
yes.
an actual limit on the hops, because you can have a packet that's hopping quickly, right?
Yes, of course, of course.
But then it won't be stopped because it exceeded a certain amount of hops.
But that's why it's usually the number of hops rather than actual time, because if it was actual time, then if it was going through a slow node, then it could have wasted a lot of time in that node, that queue, and therefore it will end up dying later on. So usually what they would use is number of hops, really and truly. However, it depends. It depends on the implementation. You can use either or, really and truly. I mean, you can have a time to live, which is in number of seconds, in order for it to actually reach a particular destination. You know, or else you can say ISMA, if it's going through a number of hops, which is excessive, then essentially you have a connection which is not as direct, and therefore going to
Not ideal.
Not ideal, yeah. So
Unwanted more than not ideal. Okay, all right. So that's the context. Then you're kind of in control, and there's A to B, and you know that packets have to be sent from A to B via, for example, a firewall service, and that's it.
usually
usually
when you have a connection established between one computer and another, until that that connection is established, you wouldn't actually know how long packets are actually going to take in order to reach from the source to the destination. All right, because obviously, unless you have a predetermined route, all right, established, you're not going to know how long it's actually going to take. Once you receive the acknowledgement and you know essentially how many steps it actually took in order to reach that particular destination, then or how long it actually took in terms of time in order to reach its destination, then you could be able to say, all right, let me give it a grace period of a couple of seconds over and above. Let me give it a couple or a grace number of hops over and above. And you say, if it exceeds that to a certain extent, then you can say this packet is going to be dead. To resend it. To pull. You'd be surprised how many times your computer is actually resending packets that it has already sent in the past. Not only once or twice. You can do it quite a number of times.
Okay.
All right.
It clears it up. It gives it a bit of a context behind it. Okay, thank you.
Okay. Any other questions, guys?
No.
All right.
All right.
All right. So we'll stop it here for today, and we'll see each other next time round. Okay, guys.
Thanks a lot, sir.
See you.
No, sir, thank you.
Thank you.
Bye, bye.
Good night.
Yeah.
Bye.
Good night.
Bye.